So when last we spoke, we were talking about Newton's law of universal gravitation. The formula for it was written this way because Newton figured out that it depended most likely on the inverse square of the distance between the two objects. So r equals distance between m1 and m2. M1 and M2 are the masses, and G is equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And so we can do a few things with this. For one thing, we can say, well, how does this relate to the normal formula we've been using for the force of gravity, which is just mg? And the answer is, well, if you want to know the force due to the Earth on some mass, like that, right? The force due to the Earth on mass, that's just g times the mass of the Earth times the mass of that object, whatever it is, divided by the radius of the Earth squared, assuming the object is sitting on or near the surface of the Earth, right? The radius of the Earth is 4,000 miles, so if it's within a few miles of the surface of the Earth, this is going to be what the formula looks like. And so you can just pull this piece out and evaluate it. And so for all objects on Earth, we just get F equals mg, where g is equal to g times the mass of the Earth divided by the radius of the Earth squared, and that's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. That's what g is, times the mass of the Earth, which is 6 times 10 to the 24th kilograms, all divided by the radius of the Earth squared, which is 6.37 times 10 to the 6th meters squared, right? And if you evaluate that, that comes out to about 9.8 meters per second squared. And so that's why we just use little g, because all the objects, for all of the objects near the Earth's surface, all these terms are going to be the same, and they just evaluate to this. So if we wanted to calculate the acceleration of gravity on the moon, we would just evaluate g times the mass of the moon divided by the radius of the moon squared, or 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of the moon, which is 7.35 times 10 to the 22nd. Notice, by the way, that's about 1% of the mass of the Earth. The Earth was 6 times 10 to the 24, and so the moon is actually quite a small mass compared to the Earth's mass. Divided by the moon's radius, which is 1.74 times 10 to the 6 meters, which is about a quarter of the Earth's radius. And then you got to square that, and if you evaluate that, you get g for the moon is 1.6 meters per second squared. So its acceleration of gravity is about 1/6 of what it is on Earth, and so we'd all weigh a lot less and be able to jump a lot higher. So let's look at this formula for a second. We could say, look, the force of gravity is g times the mass of the Earth times the mass of some object divided by r squared. And so we can talk about this for an object that is maybe not on the surface of the Earth. So if this is the Earth, right, and now my object is out here somewhere, right? Now I can't just pretend that's the radius of the Earth anymore. If I want to figure out what the force of gravity is on this object, I have to actually include that distance, which is r. If it's very near the surface of the Earth, then it doesn't matter if I pick that distance or r. They don't differ by enough to change the value of the force. But so I can ask this question, suppose my weight on Earth is, so say I weigh 100 kilograms, then my weight would be 100 kilograms times g, and so the force of gravity is 1,000 newtons on the surface of the Earth, right? Right, so instead of being standing on the Earth where my weight is 1,000 newtons, maybe I can write that one a little clearer. 1, 0, 0, 0 newtons. Maybe that's a little clearer. Anyway, if my weight was 1,000 newtons, standing on the Earth, what's my weight twice as far away from the Earth's center? And so we can just look at this formula and kind of figure that out. We can say, well, again, if I'm standing here, right, and my distance is the radius of the Earth, then if I'm floating out here somewhere, right, where that's RE, and this guy's 2RE, right, then out here, so it's g times the mass of the Earth times the mass of me. And remember, my mass doesn't change between here and here, right? Your mass is the same, it's your weight that changes, right? And so I still have the same mass as before, and then, but now my distance is 2RE instead of RE, and so when I square that, I get at position 2, I get here, the force of gravity acting on me is g times the mass of the Earth times the mass of me divided by 4 times the radius of the Earth squared. In other words, I expanded that out, and this is equal to 1/4 g times the mass of the Earth times the mass of me divided by radius of the Earth squared. This is the thing that I just said on the last slide is 1,000 newtons. This is my mass on the surface of the Earth. It's g m over the radius of the Earth squared, and so my force of gravity on me is 250 newtons, because it's 1/4 times 1,000 newtons. In other words, by going twice as far away, I reduce my weight by a factor of 4 because the radius, the distance goes is squared. Right. And so, see if you can answer this question. What's my weight at 3 times the radius of the Earth? Right? I can ask another question a little different than this. I can say, suppose I can say, so one question you can see if you can figure out on your own is, what is my weight at 3RE instead of 2RE? And my next question is, suppose the Earth's radius were reduced to RE over 2. In other words, its radius was half its current radius, but its mass was unchanged, right? And so we want to know what would the force of gravity in that case be. So in that case, the force of gravity on me is g times the mass of the Earth times the mass of me divided by r squared. But now that's g times the mass of the Earth times the mass of me divided by the radius of the Earth over 2 squared. And so this becomes 4 times g times the mass of the Earth times the mass of me over the radius of the Earth squared, because when I square that I get re squared over 4, and denominator to denominator becomes the numerator. This is equal to 4,000 newtons, because this is just, this piece here is just my weight on the surface of the Earth. So by reducing the Earth's radius by a factor of 2, I get 4 times the gravitational force. You can see if I reduce the radius of the Earth by a factor of 10, I would get 100 times. If I reduced it by a factor of 1,000, I would get 1,000,000 times. This is what happens as stars collapse. The gravitational force at their surface goes as the square of their reduction in size. And so this is how we get neutron stars and black holes that require enormous speeds to escape them, because the gravitational force goes up as the square of the reduction in the radius.